the rotating magnetic field, what we saw yesterday, how the resultant magnetic field given, which is going to induce a voltage in the rotor, IM rotor. In IM rotor, there will be a voltage induced in the, whether it is a squirrel cage motor or wound rotor. This magnetic field will create induce a voltage. Okay, because of that, the voltage will be. We know that the coil in the induction motor is short circuited. If you see here, because this is coil 1, I say C1, C2, C3. This is a three phase. One end is, both the ends are short circuited. You can see that whether it is the cage rotor, squirrel cage rotor, or in wound rotor also, finally you can see that you are adding additional resistance apart from the coil resistance through slip ring. Finally, end is short circuited. This end also short circuited. So that means we are not supplying any voltage to the rotor of induction motor, whether squirrel cage or slip ring. Both the end of the rotor coils. You have single phase motors also, induction motor, but we will talk with three phase here, easy to understanding, but it can be extended to single phase also. So both the coil ends, all three coil ends are short circuited. Now, as I told you that since we are supplying a current here, voltage, we are supplying RGB three phase voltage, the current IR, IG, IB. So it creates as phi R, phi G, and phi B magnetic flux. Because of this, we are getting resultant magnetic phi R, correct? So depending upon what is the value of, that's what we saw yesterday, sinusoidally, this is itself, voltage, current, everything is varying sinusoidally with respect to time. So each phase. So resultant vector, we saw that magnetic flux created by stator is phi R. That's what we saw. This is going to cut the rotor coils. So rotor also, there's a voltage is induced. Okay. So once voltage is induced, we know that if there's a coil, you have a coil, and if the coil is short circuited, and if there's a magnetic flux, I say phi, there'll be a voltage induced. We say V induced. Because of magnetic flux, this is a time varying magnetic flux. If it is a constant magnetic flux, it will not induce voltage. Please see that if the phi is constant, DC magnet, no voltage will be induced in the coil. Even though magnetic flux is one, there should be a d by dt of phi should happen. That happens, as I told you many times the last 2-3 days. One is, I have a constant magnetic flux. I can move a coil. This is my coil. Coil is moving. Magnetic flux is constant. Phi is constant. The wire is moving. Then also d by dt of flux are cut. Then voltage will be induced in this coil. EMF will be generated. Or my wire is constant. Magnetic flux is varying. Sinusoidal square, it is time varying, correct? It is a time varying magnetic flux, but because AC current, automatically a voltage VEMF will be induced in the wire. This is the basic principle of AC voltage and magnetic field. Transformer, induction motor works based on that. So since three phase in magnetic flux is supplied by the stator, then in rotor, voltage is induced, three phase voltage is induced in the rotor, and since the rotor coil ends are short circuited, automatically current flow, three phase current flows. Okay, because of that, it creates again three phase magnetic flux. Please, that I say that this is phi R rotor, correct? This is IR, rotor current. This is VR, rotor voltage. There are so you are getting. So the current generated due to each phase, I can say that IR is going to be IM into cos omega t. I can say that IB is going to be IM into cos omega t minus 120 degree, because you know that the stator coils are physically shifted by 120 degree, and the input voltage also, three-phase also, there's a phase of 120 degree phase shift is there. So because of that, the current induced in the rotor, and because the current flowing in this also will be same, three-phase will be shifted by 120 degree with respect to each phase. So this is the three-phase current going in the rotor. Okay. Now, because of that, again, we know that it creates a magnetic flux. I say phi R, phi B, and phi G, and they will be again 120 degree apart. You can say that, I can say that this magnetic flux phi R is K into IR T into cos omega T. Phi B is going to be, K is called magnetic constant, into IB into cos omega T minus 120 degree. Magnetic flux also, you can see that automatically phi G is going to be K into IG into cos omega T minus 240. Phase shift is going to be there. So the three voltages are induced in the rotor coil, whether it is a squirrel cage or wound rotor, and there will be a current will be flowing due to this induced this one magnetic flux. This magnetic flux is going to interact with the stator magnetic flux. I say the stator magnetic flux also, you have three-phase magnetic flux. They will then you are getting resultant magnetic flux or resultant. With that, this is going to interact and the magnetic torque is produced. That's how it works. Okay. So basically, we are going to get a torque at the induced torque. We call it induced torque in the rotor. Induced torque in the rotor. For example, before going further, we wanted to know, when we talk of induction motor, two more terminologies I wanted to talk. One is called as a slip. Correct? Slip. Other one is slip speed. Okay. We are going to see two things in this one. One is called slip. Other one is called slip speed.
Sir, I have a question. Can I ask if you allow me?
Definitely, please.
Professor, in the last class, you have taught us regarding synchronous motor. Okay. And you have taught us that three-phase current is provided in the stator, and a DC supply is provided to the rotor.
Correct.
And by aligning that, the rotor is chasing up the rotating magnetic field, and hence by that way, synchronous motor works. Right?
Sir? Correct. Yeah, correct. You are correct.
Yes, sir. So precisely what I got from that concept is that for starting a synchronous motor, we have to have a external DC supply to the rotor, right, sir?
Yes.
Now, if we come to induction motor for time being, so here you are teaching us that we are providing three-phase like current to the rotor.
Yes.
And there is no external supply needed for the stator as well.
Rotor.
There is no external supply needed for rotor, right, sir?
Yeah, correct. And so the magnetic flux in the stator, which gives resultant, that is going to induce a voltage in the rotor coil.
Okay, so
that's why I say it is like a transformer. Transformer primary only you are giving voltage. Because of the primary voltage, there's a primary current. Because there's a primary magnetic field, that magnetic flux will cut the secondary coil. Here, secondary coil nothing but rotor. So that's why induction motor I started with the transformer.
Right, sir. So the question I want to ask precisely is that like induction motor, hence induction motor is a better like evolved version of synchronous motor in that sense.
Yes, it is better. That is why it is used. You only one power supply. You don't need additional power supply, and construction is simple, correct, rugged, and it works similar to synchronous motor. It is a constant speed motor. Correct. It depends on supply frequency. Same. You are going to see the same equations. Almost same equation like what we are going to see, slightly modified. Correct. We are going to see new terms like slip speed, all this thing. That's why I wanted to tell the new information to you.
Okay,
Sir, one
thank you.
question from my side also.
Yes,
Sorry
please.
if it's not part of the discussion, but in ICE engine we will have friction torque, right?
Yeah.
Usually we will not have that concept when we are talking about electric drivetrains. How do we account for mechanical friction in case of motors, sir?
No, so the power or torque generated by the magnetic flux interaction is called induced torque. We call it tau D. In electrical, this is called induced torque at the rotor. Induced torque in the rotor, correct? This is created, this is called a starting point. Then you have, because of this, and there's a rotation. Rotor is rotating, correct? I say omega R. So then because of this power, we can say the PD or P induced. This power is equal to induced torque, and due to what is the happens, we call this induced torque. But this torque is not going to be same as in the shaft. P shaft will be always lesser than induced torque. I can say that always because there are other losses. In fact, today I am going to teach about that. What is the power generator? What are the losses? What is the final shaft power is coming? There are equations you can, for electric motor is there, we can talk about it.
Okay.
We are going to talk about that.
Thank you, sir.
Good thing you asked. Okay. Okay. Now that we are talking about that, so the torque generated in induction motor, the basic equation T equal to 3 divided by, we are talking about 3-phase, 2 pi ns multiplied by S into E2 square into R, take down this formula, and R2 square plus S into X2 whole square. Okay. Where the S is called a slip. S is called a slip. It will vary from 0 to 1. The value can vary from 0 to 1. And when the rotor is at standstill, that means you supply voltage to your rotor, stator, 3-phase, and it produces magnetic flux at time t equal to, the rotor still not yet started rotating. We call this rotor is at a standstill. Correct? Rotor is at standstill. You applied voltage to the stator coil, but rotor is not yet to stop because torque production, because of mechanical inertia of friction, all those things take some amount of time to accelerate. Because of that, we say that rotor is at standstill. When rotor is at standstill, the slip value is 1. When rotor speed, because I told you we have two speed. One is called the synchronous speed. Synchronous speed of stator magnetic field, we call as this one. Then other one is called rotor speed, speed of rotor. Correct? Speed of rotor is always lesser than synchronous speed. Okay? That depends upon slip value. Correct? The slip, when slip is 1, the difference is maximum. When slip is 0, that means ns is equal to nr. This is rotor speed. Rotor which is kind of mechanically rotating. This is the synchronous speed of the magnetic field. Stator magnetic field. Both will never reach this one, but it can happen if you say there's no friction, all these things are there, but it never happens. The slip will be there. Because of that, the rotor speed is always lesser than the synchronous speed. Okay. So in this formula, this is the full formula for suppose if somebody asks you to find out torque developed in 3-phase induction motor, the torque developed is 3 divided by 2 pi. 2 is a constant, 3 is a constant, pi is a constant. N is the synchronous speed. We know that ns equal to 120 f divided by p. Already we know that what we saw in the synchronous motor, 120 is a constant, F is the supply frequency, 50 Hz, 60 Hz, 100 Hz, whatever, and P is the number of poles. If these two number, automatically you can find out from this. Okay, once that is known and the slip value is known, then you will be able to find out what will be the motor speed. Okay, so the motor speed can be computed using this slip and slip equal to, correct? In fact, there are two things, slip and slip speed. Slip speed equal to ns minus nr. Correct? Already I told you nr is the actual rotor speed and ns is the synchronous magnetic field. Then slip s equal to, okay, slip s equal to ns minus nr divided by ns. Okay, this will vary from 0 to 1. Many times slip will be represented in percentage. In that case, what will happen is this will be multiplied by ns minus nr divided by ns, whole thing multiplied by 100 is slip in percentage. Okay, the slip in percentage decides, okay, what will be the shaft speed. Okay, slip will go to this decide. Okay, now when we talk about the induction motor, okay, as I told you that we can take up some simple problem and try to find out how to compute the slip speed and the rotor speed, slip percentage, everything. Correct. Another thing before going further, I want to talk about the torque versus speed curve of the induction motor. So this is the torque is in the y-axis, x-axis is the slip. First we will talk about slip. Slip varies from 0 to 1. Okay. If you see the curve for induction motor torque curve, and it can vary sorry, this is 0, extremely sorry, this end is 0, this is 1. Slip varies from standstill means 1. Otherwise, let me clear this. You can slip equal to 1, here it is 0. Slip varies from 0 to 1 to 0. Standstill to when the rotor catches with the synchronous speed. When both are equal, rotor speed and synchronous speed of this one. We can say that my torque curve, if you see the torque curve of induction motor, this is around 0.2 slip. This is 0.5. Okay, I can say 0.5. And this is 1. This is 0.75. Okay. So the torque will be flat up to 50%. After that, slip, after that it start increasing. It peaks at 0.2. Maximum torque is generated when the slip value S equal to 0.2, and then it will start dropping quickly. It drops quickly like this. This is the torque versus slip curve. Okay, and we can say that the peak maximum is 160%. Yes, please.
Sir, just one doubt. Why in the...
Yeah, yes, please.
Sir, am I audible?
Yeah, you are audible. Yes, please.
Sir, the x-axis, why we have to take from 1 to 0 for this graph?
Yeah, because slip you can take anyway. But this slip varies from 1 to 0. Okay, so torque reaches maximum when it is 0.2. Generally, this is how they draw the curve. You can reverse also, you can do that means the torque becomes 0 when slip equal to 0. It reaches torque becomes 0 when slip equal to 0. That means NS is equal to rotor. Rotor is catching. That means there is no pulling power. Magnetic lock, then torque will not be produced in induction motor. There has to be slip, and the maximum torque happens at the slip value of 0.2 in induction motor. That will be 160% of this one. Okay, so
the center of the x-axis is 1 or 0 also is there. So that is what we are feeling some.
No, not 0. I want to put 0.5.
Okay, sir.
Correct.
Now
it is, yeah. This is 0.5. I started writing 0.5, then I thought why I wrote below.
Understood, sir.
Okay. Then another thing is maximum torque you can do is 160%. That peak torque. For example, if I say induction motor, 100 Newton meter is the normal torque, and you can get a maximum 160 Newton meter at slip of 0.2. Okay. So, and you can see that this is the another advantage of the electric motor. That's why it will compared IC engine. You can see that at 0, what is this? Slip equal to 1. Slip equal to 1 means the NR equal to 0. Correct? NR equal to 0, NS has some value. Correct? So that means rotor is not rotating, that is a standstill. We know that in all automobile, during starting, when I wanted to move the vehicle from this one, we say static friction. Correct? Static friction is maximum when the vehicle is not moving. That means the engine is not moving, or the electric motor rotor is not moving. That time it develops maximum torque. You can see that. But in case of IC engine, the torque will be go something like this. Correct? So IC engine torque, this is the max torque at particular RPM. X-axis is one. You can see that at standstill, engine torque is 0, but in electric motor it gives that almost maximum torque. Correct? Almost close to maximum torque. Okay, that is one of the advantage of the electric motor, that the speed graph itself you can understand it, which is not there in case of IC engine. So that's why we go for electric motor. Okay.
Sir,
yeah.
One more doubt.
Yeah, yes, please.
Sir, torque to speed or slip, sir? I think it is a speed. I think so, sir.
Which one?
The torque, the x-axis is speed or slip, sir?
Slip. See, that's what I said. When slip equal to 1, you have the maximum torque. That is, it produces almost close to 10% torque. X-axis is slip, not speed.
What about the speed, sir? What about the speed, sir?
Speed curve I will draw later.
Right.
Okay. Then, if for example, I have an induction motor, correct? And it is run by F equal to 50 Hertz supply frequency, correct? And number of poles, P equal to 4, number of poles equal to P equal to 4, and we can calculate synchronous speed. And it runs with a slip, correct? Slip equal to 0.5. It can anything. I told you slip can be 1 to 0. 0 very rare, but because rotor speed will not be same as stator rotating magnetic field, because rotor has a mass, there's a friction, as a Raushan somebody asked, there will be friction, bearing friction, wind friction, all these things. That means the rotor will be lagging behind the speed, rotating magnetic field. NR will be always lesser than that way. Automatically, that means some speed. Slip will be there. Maybe 0.1, 0.05. Slip can be even 0.05 or 0.1, something like that. Even at no load condition. Because the rotor mass is rotor magnetic field is trying to catch the rotating magnetic field, stator magnetic field, IS. But that doesn't happen because rotor has a mass, bearing friction, wind, internally there's a cooling air is going on the motor. All this thing creates some of the friction. Due to that, the rotor speed is always lesser than stator, so automatic slip comes. Already we know slip equal to NS minus NR divided by NS into percentage. So slip will be there. Slip never becomes 0. Correct? It will be 0.05, 0.02, or 0.01, something like that. Okay? But it can go up to 1. 1 means that rotor is not rotating. When starting condition slip equal to 1. So now I can say that I can give any value, slip value, 0.2, 0.5, 1, something automatically you can find it. So NS is equal to, we know that 120 F divided by P. So 120 into 50 divided by 4, this is going to be 1500 RPM. So synchronous speed of the magnetic field, correct? This is called sync speed of the magnetic flux, NS. Okay. Already I given S equal to 0.5. We can find out NR, that is rotor speed. This is rotor speed, rotor speed. You can say that rotor speed or shaft speed NR equal to NS multiplied by 1 minus S. This is the formula, you can note down. So we know that 1500 into 1 minus S equal to 0.5 already given in this problem. So you can say that it is going to be 1500 into 0.5. So that means my rotor speed NR will be 750 RPM. Okay, so the same thing, if I say that my slip equal to 0.2, correct? Slip increases when load increases. Please note that when water load increases, slip increases. When water load reduces, no load condition, slip will be very small. So in this case, the water speed will be close to synchronous speed. So if I say this one, automatically you know that it is the NR for slip equal to 0.2 is going to be NS multiplied by 1 minus 0.2 is going to be 1500 multiplied by 0.8. Right? So if you compute, you can maybe 1500 multiplied by 0.8, 1200 RPM. So that means this is a light load condition. The motor may be running at 1200 RPM. Okay, depending upon. Okay, so this is how you compute. And then another thing we already talked about is that is slip speed. Correct? Slip speed is going to be NS minus NR divided by NS. Correct? So we say that NS is 1500 and for slip equal to 0.2, when S equal to 0.2, we know that the NR equal to 1200, just we computed. So that means 1200 divided by 1500. So then you will get the value, whatever value you can compute. For example, I computed another value, for example, slip equal to, correct, 0.05. Please tell many times the motor will be running with less than 0.1, most of the time. There are chances. Okay, so slip is 0.5 or not 5, then NS already same 4-pole motor, this one we know that 1500. The NR is going to be 1500 but 1 minus 0.05 is going to be 1500 into 0.95 and this is going to be NR, rotor speed. Our motor speed is going to be 1425 RPM. Right? So for this, the slip speed, if you want to compute the slip speed, it is going to be 2.5 hertz. If you compute 2.5 hertz. Okay. So this is few things that I want to know.
Sir, one.
Yes, please.
Can we go to the previous slide?
Yes, please.
Where we have no, just one more slide, please. One more slide back. Okay. Sir, basically you have told that if slip increases, then load will increase also, right, sir?
Yeah. Slip increases because load.
Exactly, sir. So that means load is nothing but the torque produced by the motor. It has to be equal to load, right? Then only it will be able to sustain it.
Yeah. Yes.
So, sir, here if you look at the graph, sir, basically we are seeing that the load, if the slip is decreasing, the load is increasing, clock is increasing, sir. I think that is not the matching the theory that we have like learned now. Are you getting what I will say is,
Okay.
if slip increases, then the torque load will increase. Load increases, the torque will also increase as per the motor. Here we are saying that if we are reducing the slip, then only torque is increasing. Is that not in sync with the logic that I have taught, sir? I'm sorry, just a question came to your mind.
Yeah. No. See, another thing also just wanted to this one. The torque equation, see in the torque equation what we saw. Correct. Here S means slip. Correct. In this equation, you can see that slip is part of the torque motor generator.
Yes.
Okay. So you can see that it is in the numerator as well as the denominator. In the denominator is S square. Right? Because R2, in fact, I thought of explaining about the equivalent circuit as we come back to that. Okay, where R2 is called rotor resistance, X2 is called rotor reactance, and U2 is the rotor voltage, induced voltage, and S is the slip, and NS is the magnetic flux or synchronous speed of magnetic flux.
Okay, sir. So, but the thing is that, sir, this graph and the logic is not getting synced actually in that way.
Okay.
That's the only point I wanted to say.
Definitely. Your point is well taken. We will do basically the torque equation. Torque using motor depends on slip also in the induction motor. And the torque equation gives S square. The numerator is S, the denominator is you have S square term. Because of that behavior is coming.
Okay, sir.
So we will come back. I got you on this one. Definitely I will explain to you.
Sure, sir. Sure.
Okay. So now we have seen this one, but next time I wanted to talk this about the induction motor, the electric motor specifically. We are talking about equivalent circuit of the torque. How do you arrive at the torque? Right? Torque, when you talk about what you call as equivalent circuit of induction motor. IM. I already told you the induction motor can be compared as a transformer. Okay. So this is all about equivalent circuit. No doubt. So it has stator coil and rotor coil. And coil actually the coil is simple, but it has resistance and inductance. So this is called as equivalent circuit of the coil, one coil, stator coil. Stator coil resistance is called as R1. This is called as X1, JX1, because it is imaginary part, that's why they put JX1. And then small thing. Resistance, sorry. This is the resistance and there's an inductance. I will explain what it is. First, you take the circuit, the equivalent circuit of the okay. We are applying a voltage. Okay, I can say that V1. Okay, this is input voltage applied to the stator, and because of that, there's a current flow. I call it I1. That is stator phase current, they call it. Because three phase, we are showing one phase, so it is called stator phase current. Current, because of this voltage applied across these two terminals, so there is a current flowing in the circuit coil. So this is equivalent circuit R1. And this is called stator. R1 is nothing but stator winding resistance. And X1 is called reactance. Winding, stator winding reactance, because inductive effect. Okay. Then this current coming here, I1, it divides into two parts. One is called IM, the other one is called I2. I2, okay, you can note down, I2 is called rotor current referred to stator. Because of the stator, we are not supplying any current. Actually, all the power is supplied from the rotor. Stator induced current is used. That current is produced due to magnetic field created by the stator coil. That the magnetic field is created depends upon the current I. That depends on, that's why it is called I2 is called as rotor current referred with respect to stator, and IM is called as magnetizing current. It's called as magnetizing current in the stator coil. Stator coil. Okay. Then here you have the voltage. This voltage we call as E1. Note down, this is the terminology we are using. This is called E1 is called as air gap voltage. It's called as air gap voltage. And now I2, this is I2, correct? This is IM. We know that I1 equal to IM plus I2. Okay, that is one thing. Then this is the status. The rotor part I am drawing now. Okay, so please note that this is equal to a transformer, correct? So just to understanding purpose, your voltage is E1 is applied in the stator final. That is going to induce your voltage in the rotor. That voltage called ER. The voltage induced here is called ER. This voltage in the stator coil. This represents, as I told you, that you may imagine that this is a transformer. This is called magnetically coupling, correct? Magnetically coupled. Stator rotor magnetically based. Energy from the stator is supplied to rotor magnetically. Yes, it's a induced voltage. Because of this induced current, this voltage is called rotor induced. ER is called as rotor induced voltage. Due to the current supplied by the stator completely supplying E1. Okay. Then this is called as JXR. JXR is called as rotor reactance. Because it is an inductor. Because rotor coil is a resistance. This is called as RR. RR is rotor resistance. The whole thing is called as equivalent circuit of induction motor. Okay. So it will basically works as basic transformer. So now we are on this circuit, and this can be, there are two parts, and this can be, this equivalent circuit can be. Can I go to the next page?
We are noting it down, please.
Yeah, I can go to the next page. Okay. So now we can say that the equivalent circuit.
Sir, we have to note down, sir, please.
Yeah. I'm keeping. Once you are there, please tell me and we will go to next. This is called as RC. Sorry, note down. This is called as JXM. RC is nothing but core loss. RC is the core loss resistance. Core loss resistance. Sometimes it is also called as copper loss resistance. Also called sometimes they say copper loss resistance and JXM is called as magnetic reactance. Magnetic reactance is this part. Okay. So what is you are supplying input to the P1. Because of that, there is a current going inside input motor to standard motor. Okay. So this is total even is the total current. Some part of this total current supply standard winding is used for variating IM. IM is the magnetic current, correct? So this is what we are going to create the standard magnetic field. All current supply from the power supply input voltage is not going to convert into magnetic field. Only some part is I1, some part is used for creating magnetic flux and to create resistance. It becomes two parts for RC for the XM. This is a reactance on the coil. This current is used for creating magnetic flux. Now, the other part is I2. I2 is nothing but the water current which will be supplied to the water from the stator to magnetic coupling. I2 is nothing but magnetically this current is the magnetic flux in the between coils transferred to the water. Because of that, there is a voltage issues. I2 generates a magnetic flux. That because of that, water is induced voltage. This voltage is just a current. We call I2. That is IR. IR is called water current. We know that water current is generated due to the input current only. Because water is a power supply. Correct? Because of your supply input voltage, the magnetic field is created. That magnetic field is transferred between the two coils, magnetic coupling. Then your voltage ER is what the induced voltage. This voltage is divided by this impedance. We know that ER divided by zeta is called as IR. IR is water current. ER is induced voltage. We know that it is noted R square plus XR square, JXR square root. So that current is flowing. Where R is nothing but water resistance and XR is water reactance. Okay. So go to the next slide.
Sir, what is this doubt I have?
Yes, please.
Sir, when it comes to magnetic flux creation, reactance plays a major role or resistance plays a major role, sir?
See, the magnetic radiation is depends on the both combined. The magnetic radiation depends on how much energy is flowing. Current to decide the magnetic section. How much? So that is what we say. Current, we know that this equation, correct? You can say that voltage divided by impedance. Correct? Voltage divided by impedance is going to decide. See, IR, we take this one. We use voltage divided by ZR. And ZR equals to the resistance square plus inductance square. Reaction square. Okay. But one part you have to know is the XL is DSL equal to 2 by FL. Correct? But R is also OLIA. So if your supply frequency varies, the reactance varies, resistance never varies. We are supplying a voltage, AC voltage, for example, 50 hertz. I say 100 volts, 50 hertz. Correct? In that case, resistance, current resistance are different. I say that R equal to 10 volts. Correct? Voltage 100 volts. 100 divided by 10 that is current resistive part. What is the reactance part? Reactance is 2 by FL. Correct? That depends upon frequency. Correct? If frequency XL is something. If frequency is 100 hertz, it is going to be different. If frequency is 45 hertz, it is different. So the magnetic variation is proportional to the impedance of the static coil. And also water Understood. Thank you. Okay. Now this is this circuit equivalent circuit can be minimized like this. You can take this. This is called as minimized equivalent circuit. Whatever you saw. So you have this is R1, this is JX1. Please note that JX1 is a major quantity, complex quantity. Impedance, that is a complex quantity. It has real part as well as imaginary part. Correct. That equal to R plus JXL. Correct. JXL imaginary part, R is real part. Together, this is a complex quantity. That is a complex quantity. Okay. So this is going to be, this is not going to vary. R part will be fixed. JXL will vary the frequency, and also it will going to give you the phase ratio. That's why it's like the imaginary part. Okay. So this part. This can be referred. Here we are giving input voltage. This is my I1 input current. This is called R1. R1 explanation is stator, resistance, and reactance. Here also the induction R1 this stator reactance resistance. IL is current entering stator coil. That is divided into two parts. Only voltage is IM, magnetic current, which flows this is RC and this is JXM. Same terminology. But only one thing is I2 is called as rotor current and JX2 is the reactance rotor and R2 divided by S. Correct? Is called as rotor reactance. With referred to stator. Why here is that previous I said earlier, just R resistance. But in this case, I put R2 divided by S, whereas S plus slip of the motor. Slip value from 1 to 0, that already we know. Okay. So here R1 is stator resistance. One coil resistor motor and X1 is called as stator reactance per phase. then R2 is water resistance referred to stator. Per phase. We are talking phase, we are talking phase. But when get to is called as water reactance referred to static phase. Okay. So this is by the final concept. From this we can always aggregate this is my input. Okay. So this is equal to the motor. Okay. Now we understand the equivalence of all these things, and we will look at how the power of happen in induction motor. Somebody asked power on losses in IM induction motor. Okay. So you can see like a big by starting big by correct. Here power in means input power supply induction motor is can be calculated using this formula. VT into IL into cos phi cos theta. Correct. Power factor. Okay. So root 3 is the phase input to power P input equal to root 3 is terminal voltage. IL is current supply. That is IL. Cos phi is power. Cos is theta. Theta can vary from 0 to 90 degree. Okay. Cos 90 equal to 1. That means the power factor equal to this is called power factor. Cos theta is called as power factor. Power factor AC. So power factor is one is better. Correct. But lower factor is not good. But my data is inductance is good. Lower power factor can be less than 1. It can vary fine. Whatever. If you have inductive load, the power factor please note down. The power factor here power factor which is nothing but cos theta. Where theta is the phase angle between voltage and current. Phase angle between voltage and current. Voltage and current. I is called as theta. Cos is called power factor. Power factor one is good. If I have a AC voltage, please note. If I have a AC voltage, say 200 volts peak hertz, AC voltage connected to a resistive load or pure resistance, then I have a cycle E. The cycle E equal to P by R. Correct. In this case, the theta because the phase angle will be 0. That means what it means is this. I just draw this is my input voltage, my input current also in phase. That means the sides are there is no phase difference. This happens in resistive load. If I supply AC input to resistive load, current and voltage increase, there is no coefficient. Theta is equal to 0. Cos 0 equal to you know that plus 1. Correct. There is no coefficient. Maximum cos theta is 0. Power factor 0. Generate power factor. Now it is inductive load or capacity load. Power factor will not be 1. Correct. Cos theta will not be 1. Because there will be a phase angle. There will be a phase shift. What is the phase shift? Already I told you. You want to understand. This is the input voltage. Inductive load. The current will shift. Something like this. So this is an angle 90 degree will be like that. Correct. that is theta. So cos theta and cos 90 you can see that it will become 0. Correct? Cos 90 will be 0. That means generally it is not acceptable, but that happens in the pure inductance. But inductance is resistant on the motor coil, it has a resistance also. That's why R1 from J, because of that the power factor value will be very less than 0 to 1 depending upon inductance of the coil, motor coil. Correct? More inductance, the power factor will be bad. It's not. Okay. The power flow diagram you note down. Right. So the power flow diagram in motor we are talking about. So in this input power, the first power law is going to be PSCL, where SCL means stator power loss. Correct. So you can see that this equals by now after this becomes this. Some power is lost. This much power is lost through copper loss. Correct. That copper loss happens because of the power loss here. Correct. Here there are two. You can see that there are two resistances. Magnetic is RC, copper is also here. Current flows I call it because the power is restricted. Input power is basically in R1 and also RC. Similarly, it will happen if you want R2. Okay. So for single case, we are talking about stator coil power loss, which is called PSCL. First power. Next one is P core loss. P core loss. Okay. So P core loss happens in magnetic circuit. Correct. This is core loss. R1 is copper loss. This is equal to copper loss. This goes again to resistance of the magnetic power. Okay. So this is going to be after that we can say now the input power is this much and it can reduce this much because of the losses. Next one is RCL, where RCL means rotor copper loss. Okay. Then you can see the power on due to some amount of power is wasted. Next part is the P frictional losses. Bearing losses are all things. Correct. The rotor is rotating in support of any other frictional losses. Then because of that the power is reduced. Okay. Now finally about P stale losses. Stale losses are generally due to air flow. Please note that water, one end of the water is such air because of the copper loss. All these losses are going to get generated in the water. Static copper rotor very generated. That heat is being cooled. So one end of the rotor side internal which sucks air and the air is going inside the water and the irrigation stale losses are air losses. Any other losses. So this is very good. Start is not captured by tau also. There is tau load. That is load omega. Omega is water speed. Water speed or water speed multiplied by load is the final output equal to the load. That is all available. So you can see that there are 1, 2, 3, 4, 5 losses happen. I get this much input power, I get this much. Okay. This is what power delivered to duty. This is what they call power flow diagram. Note on this. If you are asked to draw power flow diagram, you can draw this. Okay. So there are equations. I just complete this problem. As I told you, the input power can be calculated. Correct. Using the formula √3 into V5 into that is input that is this one I think I mentioned T sometimes there is a terminal voltage, sometimes there are two formula in this calculation. To calculate this is one is called P equal to root 3 times VB into IL into cos theta. Otherwise, the other formula is P in can be computed using 3 into V5 into I11 into cos theta 1. Okay. So this is called a terminal voltage. This is called a line voltage. This is phase angle. Root 3 is a constant. Instead of that, if I talk of phase voltage, correct? Phase voltage, there are two voltages. Talk of three phases. I have three phases. Connected. If you see what are the three things? R, G, B, and neutral. 4 wires becoming three phase voltage. If I measure voltage between neutral and the leading phase, it is called as VDE, terminal voltage. Terminal voltage is between neutral wire and any of the phase voltage. Okay. And if I measure voltage between two phases, it is called as V phase. Phase are V phase. That means between any two phases measure voltage, that is called as phase voltage. If I measure voltage between neutral and any phase, it is called terminal voltage. If I use the terminal voltage and current, line current, then I can use this formula and compute the input power supply by induction motor. If it's just a use and input some. Otherwise, I want the static base and the problem. You can use this formula to calculate the input power. Okay. Then so we will take this formula for further continuing. Right? I'll just take 5 minutes to close this. I know the time up. Some formulas. Then we will tomorrow we'll see some problems. For example.
Sorry to interrupt, sir. Can you please explain about the difference?
Yeah. The theta 1 is the phase angle between the terminal voltage and terminal current. And this one we are talking about theta 1. We are talking about the standard phase current with respect to phase. That is okay. So this value is given in the problem. Okay. Theta 1 phi 1 VB IL or V by IL given, then automatically you can calculate. Right now, for the problem what you are doing, right, forget about this. We will use this formula for continuity further. P equal to we are getting V phase voltage and I1 is this current and theta 1 is phase angle. Then using this formula, we can power supply to voltage can be computed. Then next one is to find out I1 because this formula I1 to compute we need what is that equivalent. That is equivalent impedance of the motor can be written as R1 plus JAX. Take this formula, then one solve problem will understand. Plus RC is in parallel with JX, which is parallel with R2 divided by S plus JX2. Correct. These are the three terms. This is first term, second, third, fourth term are in parallel. This is the symbol parallel. Correct. So then once you compute this, so what you need? R1, X1, RC, and X7, and R2, script, and X2 are these parameters given, automatically you can compute J. In the problem, you will be given for that, you can compute. What that is, then you will compute I1. Correct. I1, we need to compute. I1 can compute using V by phase voltage divided by Z. Correct. Generally, we are magnitude with an angle. When you calculate this, you will get theta 1. Theta 1 is the phase difference between the voltage and current. I told you, if phase of AC voltage and the inductive circuit, automatically the phase should be there. This is my voltage, correct? V phase. This is my current, is I1. The difference is theta 1. Phase angle between this one is called as theta 1. Theta 1 people, this is the theta 1 people for Z. Z is R1, RC, R2 will be constant, but X1, X2, X1 will be depending upon frequencies. Correct? For given inductance value, you know that it is 2 pi L. If depending upon the L value, it changes. So that's why my phase angle changes with respect to inductance value and also the frequencies. Okay. So this is what the 5 value can be. You get once you calculate V5 is given. That's equal to from the electrical I1. But I1 can consider two parts. It is a complex quantity. Correct? It will have real and and we convert to this one from complex to polar. You get I1 plus angle. That angle is nothing but phase difference between the input voltage and the input this current. Input current is that current. V phase input voltage this one. So you can find out from this. So once that is known, correct? We can try this. Okay. Then next thing, just 2 minutes. I don't want to get more time. Sorry. Next is the EAG. Correct. Already we saw that. This equivalent circuit. Okay. We are talking about this one. PAG. PAG is called as air gap power. PAG is an air gap. Correct? Power in air gap. Okay. It's nothing but P in. I like tomorrow. Just take a formula. PSCL minus P4. Okay. PSCL equal to 3 into I1 square into R1. R1 is the stator resistance. I1 is the current flowing inside the stator. 3 is a constant. You can compute like this. Then so we can say PA equal to 3 into I2 square, right, like this, into R2 divided by S, where equal to split. Okay. And then you can write I2 equal to IR divided by RR divided by S. This is IR. Very sorry. It's not IR equal to ER. What one will use to divided by RR divided by XR. J XR. Okay. This can be written as ER divided by RR divided by S plus JS XR naught. I will explain tomorrow. This is IR. From IR, we can find out I2 equal to IR divided by AEF, where AEF is called as effective turn ratio. That is given effective turn ratio. Effective turn TUR ratio. Okay, one that is known, then we can tell PAG equal to this is formula. PSS, you know, PAG is given like this. Now, the next one is called PCNB. CNB is converted. Power converted is short term. Power converted from electrical to this one is called as P converted is PAG minus PRCL. Okay, PRCL equal to 3 into I2 square into R. And P convert. So P convert can be written as 1 minus S into PAG, another form. Okay, so finally, if I want to find out the P out of the water, is nothing but P convert minus P F and W. frictional wind plus P miscellaneous also. Okay. So lastly, the induced torque tau equal to P converted divided by omega m. Omega, this is substitute. Okay, can be written as 1 minus S into PAG divided by 1 minus S into omega synchronous P. Omega sync P. Mean LS can be related. So induced torque equal to PAG divided by WS sync P. I stop here. Sorry for taking little time. Tomorrow we'll do some problem because you can expect some problem from this formula. Your midterm exam has mentioned. We'll do 1 or 2 problems to solve this so that you understand better understanding how the input AC power is converted to mechanical power. PAG is the mechanical output power available in the SAP. That is proportional to the ADB air gap. See, from static supplying voltage, magnetic flux is created. That magnetic flux is transferred to the rotor through the air gap. Because between the rotor and stator there is an air gap. That how much power is transferred? That power only is converted into mechanical power, not all the input power. So, other copper also finally we are going to get SAP server, which is P output, which is always lesser than the generated power. I stop here. Please give us address. Tomorrow we can see some problems in this 1 or 2 problems. Then we will go ahead with the advantages of the synchronous motor compared to this one. Benefits all this.
Sir, can you please,
yes, please.
can you please go back to the previous slide, sir? Just tell me. Yeah, thank you, sir. Thank you.
No issue.
Sir, can you please, sir, like I2 equal to IR by coefficient, right?
I2 equal, where is that?
A
effective.
effective, okay.
Subscript effective. They call effective turn ratio or the rotor winding, all those things. That will be given by the manufacturer or they will be given the value. If it is one that is no, then IR you can compute using this formula, which is talks about resistance of rotor and inductance of the rotor. XR is this one. One that is known, automatically you can find IR, that is rotor current. From one to rotor current, I2 can be computed. Using one of the formula. We will see whether alternate formula also is there, then we can do that tomorrow.
Okay, sir. Yeah, sure. Thank you, sir.
Sorry. Okay, please take give your time before leaving. Thank you very much. See you by tomorrow.
Thank you, sir.
Okay.
Thank you, sir.
Thank you.
Thank you. Sir.